All right. We are learning about dynamic programming, right? But dynamic programming is a programming technique or a programming method, as I mentioned before. And hence, uh, how to use dynamic programming is a big question, right? Similar to divide and conquer and recursive algorithm, you know that we have many different ways to use divide and conquer and recursive functions, right? Like quick sort in a different way, or let's say merge sort in a different way. So it's very important to understand the concept of dynamic programming, but more importantly, how to apply the concept for solving a particular real-world problem is much more important, right? So remember that when we learn about dynamic programming, we have to solve an optimal problem, and we have to know how to break the big optimal solution into the smaller one. But we don't apply the algorithm recursively, because if we do that, it's the divide, concur, and recursive algorithm. And we know it will have to calculate or recalculate some smaller problems again and again. And that's why it's time consuming and memory consuming. So in dynamic programming, we have to know how to break the big problem into a smaller one. But more than that, how can we remember the previous calculation so we can reduce them instead of redo the calculation, right? So it's very important. So we need to see the overlapping, so we can, instead of calculate the results recursively, we simply reduced the one that we already remembered, okay? Um, that is the idea of dynamic programming. But let me do one thing here, and I know from my teaching experience that uh, at the beginning, the students may feel that it's so hard, right? Okay, so that's why I want you to do the following thing for me. If you have your phone, just take it out, scan the QR code. It will bring you to a survey, and you just have to answer 3 questions there. So I will know what is the situation and how you are doing in this concept, and what else I have to do in order to improve your learning. Okay, so pull out your cell phone and then answer the 3 questions I have. All right, so I just received 2 responses. Okay, 1 or 2 more, please. Okay, very good. So it looks like it's not very hard, right? So it's still manageable, but obviously, all of you want to have more hands-on practices. Okay, so let's go back to the hands-on practice I gave you on Tuesday. Okay, so I will go through that 2 problems, and you see that. Let me bring it up here. Yeah, and you see that for dynamic programming, we have 2 different algorithms, one for matrix chain multiplication and one for the assembly line. Maybe I have to blow this one up a little bit. Okay, so that said, I wanted you to practice on this problem for matrix multiplication of matrix sequences, right? And then we have another one for the assembly line. The only difference I have here in comparison with the lecture note I gave you is that here I want to find all optimal path, right? Okay, I guess the first one is simple, right? How many of you finished the first one correctly, comparing with what I gave you as the answer? So just type in, I did, okay, very good. So how about the other one? Jared Martin, yes, very good. How about you, John and Brian? Okay, very good. Brian, did you do it correctly for this hands-on practice? Okay, then you have to practice that, okay? Okay, sorry to hear that, but I mean, it's a virtual class, or more precisely, an online class. So even if you sick, I mean, last Tuesday, you can still catch up with what we are studying, right? So in that situation, just try to work this one out and don't look at the answer yet, okay? Until you finish it by yourself. Okay, very good. So now let me. Oops. Okay, let me bring this one up. So all of the algorithms that I teach in the class, in fact, I implement all of them by myself. So I will be sure that all of the practice, all of the exercises, all of the practices will give you the correct answer, right? And also, I will try many different ways to design a better algorithms by doing it by myself. And I have everything here using a programming language we call Maple, okay? Same thing for Mathematica. Actually, I was a software developer for the softwares, right? Maple and Mathematica. So here I have the algorithm for matrix chain multiplication, all right? And the algorithm is exactly what I gave you in the class. right? And then for the hands-on practices, here's what I have. Okay, so this one. So when I have the sequence of matrices like this, then the results I have is here, right? So that said, we have, say, 29 is the smallest number of element multiplication, right? Okay. And then here is what you have, right? So based upon the results here, we can put the practice brackets here. We put it 4, right? So we put it 4. So 1, 4. Okay, 1, 4. We put it 2, right? So that's it. We multiply this 2 first, and then this 2, and then finally we multiply with the rest, right? So this one is very straightforward. Yeah. All right. And now, when we come to the assembly line, and in fact, you can see from here that I have many real-world problems that we can use dynamic programming. For example, activity selection, right? And then assembly lines and optimal binary search tree and Young Tableau, right? And then graph theories also, we can use dynamic programming. So I just picked some problems that is very, let's say, helpful for your future, say, career also, right? So for example, right now is trendy, right? Actually, it's a good trend for dealing with computational biology, like we have for the vaccines for COVID viruses, right? And then we also have right now the say digital coins, right? That is what we will learn next. So now let's go to the assembly line. So here I have 2 lines, but in fact, I have programs that can deal with 3 lines, 4 lines, no problem. Okay, we just have more. We just have to modify the program a little bit. So instead of dealing with 2 assembly lines, we can deal with more than 2. Okay, and then here is what we have for this. Here is an example I used in the slides. And then here is what I gave you for the hand-on practice, right? And you can see here that when we have these 2 assembly lines, I have the smallest smallest time is 27. And here, when I fill up the arrays, you can see here that there are 2 options. Okay, if we can go with 1 or 2, because if we go with 1 or we go with 2, the results are the same, right? So that said, we can have either 1 or the 2. And here we have the same thing, right? And remember that we fill up from left to right, right? So we have the first one, we have 2, and then 2, 2, 2, 1, 1. But here we have 1, 2, 1, 2, right? Based upon the results we have from here, we can write down the results. Okay. For example, here we can have either 1 or 2, right? So if we go with 1, we go here, and then we go with 2, right? Right? And then we go with 2, and now we go with 1, and then we go with 2. Okay. Same thing, if we go with 2, right? Then from here, we just go with 2. If we go with 1, we go here, right? And then go down 2. If we go with 2, go down here, 2, continue to 2, go to 1, go back here, right? Okay? And then go down to 2. right? So if you have the results like this, then you can write down everything by writing a small, say, recursive program. In fact, we just have a stack, right? So when we have this one, push one in the stack and then continue, and then go back, and then take the other one, and then continue, right? I will give you an idea of that building up multiple sequences after we went through the longest common sequence for the gene matching today. Okay, so that said, it's a little bit different with the algorithm I gave in the slides, right? But you can think about what can we do in order to find out all possible ways, not just only one optimal solution. All right, so I will go here, and then this one is the program for today dynamic programming algorithm. Is for what we call gene alignment. Okay, so before we talk about this, let's have some background on this one. Okay, so let's have some background on the longest common subsequence. Last week I gave you a motivation about this. Yeah? So the motivation is that when we have two species or two, say, mutations of a virus, right? We want to see what portion of the genes they have in common. So we want to know whether or not, let's say, the Omicron or the original COVID-19 virus, what do they have in common? So we can design the vaccine that can attack both of them instead of just focus on the portion that the Omicron has, but the original virus does not have. So in that situation, we need to have two vaccines for the same virus, but a little bit of the mutation, right? So that's why the longest common subsequence is a very important problem, and it has many real-world applications. So the problem we have here is that if we are given two sequences, so in the computational biology, it means that we have two sequences for the genes, right? But it can be anything. We can use the longest common subsequence in, say, language recognition, right? For example, if someone writes a sentence or a word that is not 100% correct, then how can we make the suggestion for changing, right? So you see, we have it everywhere nowadays. Like when you use Google or when you use Microsoft Word, you type in a word that is not correct, right? Then they will make some suggestions for you how to correct that. But how do they make the suggestion? They have to use the longest common subsequence in order to see which one is the closest to this to the word we wrote, right? So it's another example for how to use the longest sequence, longest common subsequence for some real-world application. Okay, so it's too hot here in this room, so let me turn the AC on a little bit. Okay, so that is the motivation. So, for example, we have here is the sequence X, right? So subsequence of X can be any subset of the letters, right? As far as we go from left to right, they are still an elements of the sequence. That said, ABD is a subsequence, meaning that we can have A here, B here, and D here, right? Or we can also have A here, B here, and D is also ABD as a subsequence, right? Okay. And then we want to find out the longest subsequence in common of the two strings, okay? So that said, if you have two strings, in this situation, we can have here B, C, B, A, right? Or we can have here B, D, A, B. So those are the two common subsequences that have the same length of 4, right? So that said, both B, C, B, A and B, D, A, B are the longest common subsequence. And again, you can see it, that it's very similar to the assembly lines. We can find one longest common subsequence, or we want to find all common subsequences, right? That is, the two very closely related problems. So we will try to find one common subsequence first, and then the next step would be how can we modify the algorithm so we can find all longest common subsequence. Okay. All right. So again, to find the longest common subsequence, we can use the brute force, right? The brute force, as we know, is by checking every possibility, right? So the first thing we can say that which we have every subsequence of X, and then for each subsequence of X, we try to search on the second subsequent, the second sequence Y to see if there is a match, right? But every subsequence of X means that we have to consider subsequence with one letter and two letters and three letters and four letters, right? So the total number would be 2 power to the m, where m is the length of the sequence X, right? If we have a sequence, we want to see if that sequence appear on the second one, then we just have to search from left to right, right? So that said, it will take us n steps, because we have to go through every element of the second sequence Y, right? So in general, the running time we have is n times 2 power to the m, right? N is the number of elements we have on Y, and 2 power to the m is all of the subsequence of X, where X has m elements, right? In general, we can assume that both X and Y have the length n. Then in that situation, we have n times 2 power to the n is still exponential, right? But as we know, exhaustive search is the worst algorithm we can design. And in fact, nobody wants to have an algorithm like that or a solution like that. right? So if we have a program for finding the longest subsequence using the brute force, then for the COVID virus, it may take about 10 years in order to finish the program, right? So nobody wants to have it, of course. Okay, so we want to design the algorithm by breaking the big problem into the smaller one, right? So that's why we want to see what can we do. So we will try to see if the two sequences have the same elements. Yeah. If they have the same element, meaning that the results we have at least one common element, and then plus with the common elements of the smaller subsequence here, right? So that's it. First, we compare one element. Usually, we start the last element and work to the left, right? Similarly, we can compare the first and work to the right. We have the same, basically the same algorithm, right? But instead of going from right to left, we can go left to right. Okay, so that said, we will try to see if they have the same element. Then the longest subsequence will be reduced to compare the rest together, right? But what will happen if they don't have the same values? Okay, for example, in this case, if they don't have the same elements here, then we know that, we don't have a match here. So what we will do is that we will compare, let's see. Yeah. We will compare this subsequence with this, right? Meaning that we exclude the last one of the second sequence, and we will compare this one and the rest. Yeah. Meaning we will try to exclude one element at a time of the first sequence and then of the second sequence. And the longest subsequence of either the red ones or the green ones will give us the longest subsequence for the original sequences, right? Okay, so that said, we will break the problems into the smaller problems like that, right? And in general, because we deal with the sequence that can have any number of elements, so we will try to have the longest common subsequence of xi and yj. Okay, so same thing for y. We have y1 to yj, right? So that's it. If you have x and y, you compare the last element first and then work with the smaller one. So in other words, we need to find out what is the the longest common subsequence of xi and xj, where xi is the first I element of x and yj is the first j element of y, right? Okay, so that's it. We want to know the common subsequence of, say, x1 to xi and y1 to yj. Obviously, for the original one, we need to know what is the longest common subsequence of x1 to xm and y1 to yn, right? But then we work back with smaller subsequences, and that's why we want to find out what are the longest subsequence for the smaller one, right? So that said, if the last elements are the same, then we count it as one matching, right? And then add the longest subsequence of the smaller sequences. In this case, this one and this one, because the last ones have been matched. So if they are not matched, then, as I mentioned before, right, we have to compare this one with the whole thing and the whole thing here with this one. So in other words, if we call Cij is the length of the longest subsequence of xi and yj, then okay, this Cij is just a function for calculating the cost, right? And you can see that we can store the cost values in a two-dimensional array, right? That's why we choose the two-dimensional array like that. But in fact, we can say that this one is a function C that has two parameters, I and j, right? So we need to calculate the cost for xi and yj. Okay. Then we know from here that we will have ci minus 1j, right? That is the red one. Let me choose that color instead. Okay. First, we find out what is the common subsequence of ci minus 1 and yj, right? And the green one, ci and j minus 1. The bigger one will be the values of Cij, right? Okay, it's very simple. Okay, so that is the idea of calculating the cost. And of course, from here, you can see that Cij is calculated by comparing the red subsequences and the green subsequences. Then we need to remember, okay, what will happen if we use the red one? What will happen if we use the right one? Right? So that said, if we use the red one, then we know that we have the I minus 1, same value, right? So that said, we can choose the arrow. Again, let me choose the red one. Yeah. This one, right? Then this the same column, I mean the same row number, but the column will be reduced a little bit. So we can choose the arrows here, the upper arrow or the left arrow, to tell us that okay, the value of xij is obtained by following the first approach or the second approach or position, right? So instead of using the upper arrow or left arrow, we can choose a letter for that. That is also fine. Okay, so instead of using the arrow, we can use the letter U, and this one we can use the letter L instead of using the arrow. Okay, but let's practice a little bit, then we will understand more. And before we go into the details for how to design the algorithm. All right, so that is pretty straightforward, right? However, the complexity of the algorithm when we break it into smaller problems will still be exponential if we use divide and conquer and recursive algorithm. Okay, so here let's look at this. We know that in order to calculate Cij, we compare the last two elements, right? And if they are the same, then we add 1 into the value and then recalculate Ci minus 1, J minus 1, right? If not, then we call the function C again with J minus 1 and call the function C for I minus 1 here, right? So if we write this program, if we write a program for calculating the Cij using recursive one, it means that, okay, the base case, if I or j is 0, we return 0. Otherwise, we compare, right? If they are the same, then invoke the function C again, right? If not, then invoke the function C with ij minus 1 and I minus 1j, right? We can assume that I and j are both from 1 to n. Okay? So if we choose recursive algorithm, then what would be the complexity of this function when we calculate Cij? Or more precisely, we call CNN, right? So the final result would be, what is CNN? So how many steps would it take if we have our program or our algorithm using recursive algorithm? Here, we can assume that both I and j will go from 1 to n. So if we call t n is the number of steps is needed, right? Then you can see that Tn is what? If you look at this, Tn 2 times Tn minus 1 plus 1, right? Some extra cost for comparing if I is 0 or j is 0, right? And then compare here, right? So if Tn, where n is the length of both sequences, we can assume that the two sequences have the same length, right? If not, then we just add dummy values into the shorter one. Then we would have both of them have the same length, right? Okay, so we have Tn is 2 times Tn minus 1 plus 1. Then what is Tn? How can we solve Tn here? What is Tn? So remember that when we have the brute force, we have the complexity is 2 power to the n, right? More precisely, n times 2 power to the n, where n is the length of both sequences. Okay? So this one is for the brute force or exhaustive search. So now we design an algorithm that looks better, right? By comparing the last elements, right? If they are the same, if they are not, then invoke the function again, right? But when we analyze it, we see that Tn, where n is, the max value of both I and j, it will be here, Tn minus 1 and Tn minus 1, right? Because we reduce one side by one, right? So it's very close to 2 Tn minus 1. Okay? Or more precisely, is greater, right? Then what is Tn? Two power to the n. Very good. Yeah. 2 power to the n, right? Because this one is 2 Tn minus 1, 2 square times Tn minus 2, right? Etc. And you add some extra values, but basically it's still 2 power to the n. It looks like it's still the same like the exhaustive search, right? Not better, right? So the problem was, as we all know, that because when we have the recursive algorithm here, some values will be recalculated again and again, right? So that's why the dynamic programming comes handy. So here, what we have to calculate. We have to calculate the Cij for I from, say, 1 to m, and j from 1 to n. That means that we have to fill up the table here, right? C1, 1, 1, 2, 1, 3, 1, 4, until we have C, M, N. So in this case, we have all of the values, right? So we just have to fill up this one. But remember that if we choose recursive function, then some of the values here will have to be recalculated again and again because the recursive function will call it. And then we have to recalculate that, right? And hence, here, what we will do is that we will try to fill up this table, but we don't fill it up from here. Back, right? We fill it up from here down. So that's why we will be able to say improve the complexity a lot, right? So the idea here is that here, the values of Cij will have to be recalculated in the recursive function, but here we will try to store them. For example, we will store C11 first. Okay? And then, in order to calculate C12, we don't have to recalculate this value, but we just have to compare the values here. If they are the same, right, then we use the values here. If they are not, then we will try to see if we can use the value here and use the value here that we already fill out in order to calculate this one. So similarly, we can fill up the table here row by rows. Yeah. So we fill up this row and then fill up each row. And whenever we try to fill up this value, remember that we only use the values here of I minus 1, j minus 1, or say I j minus 1 or j I minus 1j, right? So the calculation of this cell depends on 1. Let me use a different color. 1, 2, 3. Yeah. Any values that we need to fill in this table, we only use the value from here, the diagonal, or the left, or the upper. So that said, we can fill up this table left to right, row by row. Okay? Is it the only way? No, it's not. I will come back to this point after we somehow practice with this algorithm. Okay? We need to practice with this algorithm to see how we can use the algorithm here and memorize the simple values we have first. Okay? So now here is what we have. Okay, I already talked about this. Okay, so the algorithm is exactly what I just explained to you, right? So we will try to understand this algorithm by doing a hands-on practice on this example. Okay. So we have two sequences, X and Y. Yeah. So here is X, A, B, C, D, C, B, D, A, B, right? And here's Y. Okay. So we try to build up the table for Cij. Okay, here is what we have for Cij. Okay, C1, 1, 1, 2, 1, 3, etc. Right? But we need to have two extra rows and columns here. Okay, what does it mean with this extra? This extra one means that what will happen if the subsequence of X has no element, 0 element, right? So if 0 element in X, we try to find the common subsequence with the subsequent of Y with 1 element, 2 elements, 3 elements. What would be the values? What would be the length of the longest subsequence if the first subsequence has nothing? So it means that if the first subsequence has no element and the right subsequence the second subsequence has nothing, right? Then the longest subsequence will have 0 value, right? Okay, same thing. I think I have to change the color here a little bit. It's a little bit hard to see. Okay. All right. Okay, so here we have 0. The first string has 0 elements, then whether or not the second string has 1, 2, or 3 elements doesn't make any difference, right? So still have 0 common subsequence or no common subsequence at all, right? Same thing, if the second subsequence has no element, then regardless of how many elements the first one have, we still have the length is 0 for the longest common subsequence. So those are the steps we will take first, right? So first, we need to build up this table or this array, right? We add one extra row and one extra column. And now we start to look for this value. Okay? So C11. So that's it. We are talking about C11. What is C11? Remember that when the first string has one element, the second one has one element, we will see if they have the same letter, right? So in this case, okay, A and B, they don't have the same letter. So that said, okay, we have to use this option, right? Because they have the different values, right? So in order to calculate this one, we have two options, meaning one is by using the left and one is by using the right, okay? Meaning we calculate this Ci j minus 1 is this one, right? We use it. Let me use this one and then this one in red, right? So here we have Ci j minus 1 and then Ci minus 1 j, right? Which one is bigger? They are the same, right? And the biggest value is 0, so we write here 0. But then we have to know, okay, the bigger one comes from this cell or from this cell, right? So we can say that it comes from the upper, okay? But this is only one option, right? We can, at the same time, record the value here. It can come from this direction as well. So that said, in each of the cell here, besides writing the value, that is the length of the longest common subsequence of x1, y1, okay, we also say that, okay, the value here, we obtain that by using the one on the left or using the one above, right? So because this way means, okay, here we have the same ith, right? Here we have the same ith, but here we have, let me use a different color, right? The above row, same color, right? So that's what we have. Okay, so that is the first element we want to fill out, right? And remember that in order to calculate this one, we simply reduce the value before. We don't have to recalculate anything, right? So now what would be the next value we should calculate? Remember that any values here, we just need to look at this, and look at this, okay? So 3 cells, the 3 neighbor will be used for the calculation of the value here. So keep that in mind. It will help us to design the way we can fill up this table, right? So that is why we say that, okay, if we can finish this row and then go to the next row, we don't have to recalculate anything, but just reduce the values we fill up before, right? Okay, so that is what we have up to this point. From here, very similar manner, right? So from here, compare the two letters, they are different. So we will compare the value here, the value here, the bigger one, right? So that said, I will simply copy this and have it to the next cell. Okay. So that said, we have the value here is still 0 because we compare with the upper and the left. They're the same. So we can say that the bigger one is still 0, but we obtain the bigger one by either using the upper or the left cell. Okay. So same thing here. If we go one step further, we would have this. Okay, now when we come to this one, it's a different story, right? Okay, so for this one, they have the same letter, right? So that said, the value here will be the subsequence of the first one has 0, and then the second one has 3, right? And we know that we have a magic, so it will be 1. Not a good letter. Okay, 1, right? Plus with the cost here, we already have 0. Okay, and then what do we have? How do we obtain this one? Is from the previous diagonal, right? So that said, we can use this arrow saying that it comes from the diagonal, the previous diagonal value, right? Okay, now same thing for the next one. Okay. When we have this, when we calculate this value, A and B are different, and hence we have to compare the value here and the value here, right? The bigger one will be stored here. So we have here 1 as well, right? Okay. The number is too bad. Okay, so here we have 1, and the value will come from the left, right? Unless the previous one, we can have it from the upper or the left. This one, you only have it from the left because the left one has the biggest value, right? Okay. Now, what do I have for the last one? What value do I have for the last one? Two is 1, right? Because remember that if we have a match, then the match will be counted 1 plus with the length of the longest subsequence of the previous substrings, right? The previous substring is here. And hence, this one will be 1 plus with this value. Okay? It's still 1, right? Okay, so here we have the diagonal. This comes from here. Oops. This one comes from here. Right? 1 plus this. It does not come from the left, because it comes from the left, then it should be 2, right? So that's it. Here we have 1. Okay? All right, very good. So now let's fill out the second row for me. Okay, all of you put out a piece of paper and then calculate the values for the second row for me. So I'll give you about maybe 3 minutes would be enough. Okay, so you can type in your answer, something like C1, C21, what you have, the number, and then the next one would be, say, the direction, right? Okay, 2, 1, 1 diagonal, very good. Okay, and then the next one, 2, 2, 2, 3, 2, 4. Oops. Okay, okay. All right, so here's what we have, right? Okay, looks like you have it. Yeah, so one left, 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 diagonal left. Okay, so this one you have actually BB, then it has to be diagonal. Okay, one diagonal, right? This one we compare, then it has to be on the left. This one compare on the left. Okay, this one A and B, they're different, so we can either go up or on the left, either way, right? So this one we can either go up or on the left. Okay. So this one we have a match, so it has to be 2 and diagonal, right? Brian, what did you ask? Oh, okay. All right. All right. Okay. So, but the point here we have is 1, it should not be left, right? This one has to be diagonal because you have a match. Okay? All right. Very good. So one left, one left. One, you can either go left or upper, right? And then you have 2 diagonal and 2 left. Okay, very good. All right. So you can continue to fill the rest, right? But here comes the question. Previously, we fill it up like this. Okay, we fill it up like this, right? Is it the only way? Can we fill the values in a different manner? Can we fill it in a different manner? Yeah, we can go down, right? Okay, column by column. Yeah, we can go this way first, and then this way, and then this way. Okay, sounds good. However, either going row by row or column by column will only work well when you have one CPU. Okay, so for parallel computation, you cannot do it that way. And that's why we have the third way, that is used when your computer have multiple CPUs or even GPU. And the way for it is instead of going row by row or column by column, we will go diagonal by diagonal. We go this way, this way, this way, this way, this way. The only difference you have is that you can have, okay, here, all CPUs working on the calculation. So for example, here you calculate this one, this one, this one, this one, this one at the same time using different CPU. But if you go row by row or column by column, you cannot do it because you cannot have the first CPU working on this and then the second CPU working on this, the third one here, right? Because they still have to wait for the previous CPU. So that's why we have the third way, and the third way is the most popular way when you have multiple CPU. Is it clear? All right. Yeah, it's very neat. Actually, it is the new way. Okay, we have that idea recently. Okay, so here's what I want you to do. Take a picture of this example. It's a hand-on exercise for you. Okay, and come back here on next Tuesday, and I will show you how it works on a program. Okay, how can we design and implement the program? By the way, I saw that some of you submitted the programs, right? I want you to submit the source file, meaning the Java code or C code or C++ code, so I can run your program on the input I gave you, okay? Looks like you need an extension, right? Do you need an extension? I can give you 2 or 3 more days if you like. So you can perfect your program. C# is fine. Okay? Any program, I mean, any programming language is fine. Python, C#, Pascal, right? Okay, so I'll give you, say, 2 more days. Is it enough? Okay, 2 more days. So you can perfect your program, right? So be sure that when I run your program, I will run it on the input, the sample I gave, and I want to see if you have the same output as as what I gave you. All right. So that's it for today. And if you don't have any more questions, then take care and bye-bye.